Hi guys, in this video let's look at the oxidation of alcohols. Here we have a warm-up page and we have a reaction here, estradiol being converted to estrone in the body. We see the difference here is estradiol has two OH groups and thus can be considered a diol. And in this reaction, this alcohol group is being converted to a ketone. It's also why this is called estrone with the "one" ending. Both of these are considered estrogens, typically female hormones. Is the reaction below an oxidation or a reduction? Well, you might think it's an oxidation. That's the title of the handout. But why? Why is this an oxidation? Now, in Gen Chem, general chemistry, we typically look at oxidation of metals. And I can find some scratch paper here. We'll use here. And so if we go from maybe a lead 2+ to lead 4+, okay, we see that this would be loss of electrons. This is an oxidation. We can abbreviate that as O or OX, often shown like that. Oxidation, if we come backwards, that's a reduction, and we can typically, it might not apply here, but often we show H, oxidation, or we show electrons, but basically that's a reduction. We had oil rig, right? Oil rig. Oxidation is loss of electrons, reduction is gain of electrons, and we see that from oxidation states. Okay. But how do we determine oxidation in organic chemistry, or redox in organic chemistry? Two different ways, and it's illustrated here. First off, if we look at this conversion, we have lost H's, okay? Loss of H's. Oxidation in OChem equals equals loss of hydrogens. Also equals more bonds to an electronegative atom. Two ways to judge redox in organic chemistry. If we look at what's going on here, we're actually losing two H's because the carbon with the OH group has lost an H and the oxygen has lost an H. We've lost two hydrogens. We see that's thus an oxidation. We've also, if we look at the carbon, we can see and say that the carbon has been oxidized, because here the carbon has one bond to a more electronegative atom. I can go back over here and say I need to use more twice. More bonds to a more electronegative atom. Carbon has one bond to oxygen, a more electronegative atom. Now the carbon has two bonds to a more electronegative atom. So two different ways we can see this is an oxidation. Okay? Now, oxidation of alcohols is going to make that a double bond, and that will become a carbonyl. Now, the functional group will either be a ketone or aldehyde, or some other functional group as we get into other possibilities. Okay, two main ways to judge redox in organic chemistry. If we come the other way, estrone going to estradiol, that would be a reduction, because we have, in reduction is just the opposite. reduction equals gain of H's or less bonds to a more electronegative atom. Electronegative atom. Okay, less bonds. And if we go backwards, estrone to estradiol, the carbon has 2 bonds to a more electronegative atom. If we come this way, it now only has 1 bond to a more electronegative atom. Coming this way is thus a reduction. Okay. So, other things here on this warm-up page, we'll look at oxidation of alcohols first. Later we'll move to oxidation of alkenes. Okay. Here's that same biochemical reaction coming this way, estrone to estradiol. Of course, that's a reduction. All right. And this is actually in the body catalyzed or promoted by an enzyme here. Okay, oxidation of alcohols. A primary alcohol is going to be oxidized to an aldehyde. Now the oxygen is turned, but if we remove an H from the carbon and an H from oxygen and put a double bond here, okay, I'm going to do this here, draw it the same way, boom, boom. Instead of a single bond between the carbon and oxygen, let's make it a double bond. All right, we lose an H from carbon, lose an H from oxygen. It's now an aldehyde. Now, as I said in Organic 1, aldehydes, we typically draw in the H that's on the carbon of the aldehyde. All right, there's 2 H's on the carbon here. Now there's only 1. I'm drawing it in. There's your aldehyde. But that and this is the same thing. I just have turned the oxygen to point it up. Okay, so that's all that's going on there. We're losing 2 H's and putting a double bond in, an extra bond between the C and the O. That's your oxidation. And that's the result of oxidizing a primary alcohol. Now, aldehydes can be further oxidized. It requires the presence of water. And when they're oxidized, you actually get a carboxylic acid. Now, we don't put a triple bond between the C and the O. That's not possible. Instead, we end up with an extra oxygen bonded to the carbon, and we see that's an oxidation because here the carbon has 2 bonds to a more electronegative atom, and now the carbon has 3 bonds to a more electronegative atom. We didn't add H's. You don't have to do both of these. Okay? Either one of these constitutes oxidation. All right? This does require water. That's where the extra oxygen comes from. We'll look at that mechanism. Now, if you oxidize a secondary alcohol, just put the double bond in between the C and the O, and I have the O drawn up here, I had it drawn up there, you get a ketone, not an aldehyde, because there's 2 R groups here. 2 R groups here equals ketone. Now, ketones are not going to be further oxidized in this class, in Organic 2. They can actually be oxidized, but not in anything we're going to be looking at, not with the reagents we're going to use. Perhaps they could be, but we will never further oxidize these. Okay, that would be a very specialized and exception. So for us, we're going to say the reaction stops there. Now, tertiary alcohols, if you try to oxidize them, no reaction. Because the carbon has no H to lose, and so you cannot put a double bond in between the C and the O. You would then have 5 bonds to carbon. It's not going to be done. Now, it can be done in some specialized cases, but not in this class. This is the standard oxidation of alcohols. So tertiary alcohols actually cannot be oxidized. Okay. Now, what reagents will oxidize alcohols in this manner? All right, these here, and I call these the big three. Sodium dichromate. All right, dichromate. Dichromate is going to be Cr2O7, and of course the charge is, if we show it condensed, 2 minus. And thus we need 2 sodiums or 2 potassiums. You can have potassium dichromate. All right. It's pretty complex diatomic ion. Also chromium trioxide, a little bit less complex. It's only 1 chromium. Chromium trioxide is a neutral molecule. Okay, in itself it does not require a countercation. Also KMnO4, potassium permanganate. And potassium is the most common with permanganate. These all are sort of metal reagents with lots of oxygen. That's sort of a key indicator that they're oxidizing reagents. Okay, oxidizing reagents used in the laboratory, okay, where your body uses enzymes, okay? Your body doesn't use heavy metal oxidizing agents, and these are typically heavy metals, okay? Mechanism for the oxidation. Let's look over at the other handout, okay? Where we have the big three. All right. Now let's focus on the chromium reagents. Either of those in the presence of aqueous acid, typically either sulfuric or acetic acid. Of course, that's aqueous. Acetic acid is not necessarily aqueous, so maybe we need to indicate that. All right. But either of these break down, or in the case of chromium trioxide, it just becomes hydrated. But both of these ultimately form chromic acid in the presence of aqueous acid. Now, chromic acid looks a lot like sulfuric acid, except chromium instead of sulfur here. And chromic acid, the chromium has an oxidation state of 6. Okay, if you can judge oxidation of metals here. And chromium 6 reagents are typically orange. Now the alcohol, either primary or secondary, right, because a tertiary alcohol doesn't react here. Primary or secondary alcohol reacts with the chromic acid. It gets oxidized to the carbonyl compound. The chromium reagent gets reduced. And we can see reduction we would expect to go from chromium 6 down as it gains electrons. Now this is actually a 2-electron reduction. It first goes to chromium 4, but then the chromium 4 sort of autocatalytically reduces down to chromium 3, and that's the ultimate fate, I should say, of the chromium after it's reduced. All right. Now we're not looking at mechanism yet. We're looking at just sort of some details of the reaction or the mechanism, and focusing in on the fact that the chromium 6 orange gets reduced to chromium 3, which is blue, and your orange solution turns blue, and that's actually a visual indication that the redox reaction has taken place. Now this is thus a oxidation test known as the Jones oxidation test. Primary and secondary alcohols will turn chromic acid, which is orange, to blue. You can actually call the alcohol a reducing agent, while we call the chromic acid an oxidizing agent. It oxidizes the alcohol reduces the chromium. Okay? Now, typically in organic chemistry, we're interested in the organic product, and so we focus on the fact that the alcohol got oxidized to the carbonyl compound product. Now, because tertiary alcohols cannot be oxidized, that means they will not reduce the chromium. This will not happen. And thus they will not turn the chromium orange, the chromic acid orange, to blue. So if you combine these and you don't get a change to blue, you're like, hey, my alcohol is not being oxidized. It must be a tertiary alcohol. Assuming it's an alcohol, because there's many other things that will not be oxidized. I mean, maybe it's just an alkane. I'm assuming that you first determine that you have an alcohol. Then the Jones oxidation test will tell you if you have a primary secondary versus a tertiary. Okay? Now we got to be careful, because as we move forward, we'll see that aldehydes also give a positive Jones oxidation test. I've actually already seen that, because an aldehyde can also be oxidized, and thus the aldehyde would reduce the oxidizing reagent. Okay? Ultimately, the Jones oxidation test tells you that whatever you added to the chromium was oxidized and thus reduced the chromium. There may be other things that can be oxidized other than primary or secondary alcohols. Okay. Let's look at mechanism for this. Do I have that in a handout? I don't think I do. Really need a new notepad here, but let's look at here. I don't reckon I have this in a handout. I thought I added it. Maybe not. No. Anyway, we'll rewrite it here. Mechanism for oxidation. Okay. Not going to go full details, but just a little bit here. Let's look at an alcohol, and let's very generically consider a metal that's in the 2+ oxidation state. Any oxidation, it doesn't matter what we start with. It's the process here. Okay. These electrons, just like H+, these electrons can sort of bind here. Okay. And we would get something that looks like, okay, that's to the metal. There's an H. This is now plus. The metal is actually now just plus itself, because it's gained 1 electrons. In electron count, you count one of the electrons as belonging to the metal. Of course, if a neutral reacts with 2+, you still got to have 2+. You can't just gain charge. But now we see what looks like a protonated alcohol. Okay? Now, there's an H here. Now, let's try this here. What if something like water comes in and takes this H? These electrons move here and make pi bond and kick this off onto the metal. that would give a double bond between the C and the O. The H remains one lone pair. That oxygen is positive. We made, okay, H3O plus right here. And what's up with the metal though? The metal, now these electrons move on to the metal as a lone pair. Now what I showed here sort of looks like an E2. E2 elimination, put in double bond. And you're like, well, can you do E2? But we're not making an alkene, we're making a carbonyl. Okay? And all of our rules about E2 applies to making carbon-carbon double bonds, not carbon-oxygen. So it's E2-like. The main thing, and now something needs to take this H, we can actually have another water take it. And we would actually make another H3O plus. And so you see here, we lost two H's and we've actually generated acid. That's sort of the fate of the H's. But look here, the original metal is now oxidation state of 0. The metal is reduced. It has gained a lone pair. It gained 2 electrons. Do you see how it gained them? It took a lone pair from the oxygen. This lone pair, if you keep track of it, it becomes a bonding pair. Then it moves on to the metal. There it is there. Okay? And that's the old classical, it gained electrons. It's hard to see the alcohol losing electrons. Well, you can see it. Okay, you can see it. Ultimately, the alcohol has lost 2 H's and the carbon has more bonds to electronegative oxygen. Okay. That's sort of the mechanism, just so it's not so much magic. All right. Remember I said it was a 2-electron redox? All right, 2 electrons, okay. If this was originally metal 7+, this would be, or 6+. If it gained 2 electrons, it would then be 4+. But chromium 4+ will auto react down to chromium 3+. In some manner. I'm not quite sure how. Okay. Oxidation of alcohols. By the way, if you ever take a breath analysis test looking for presence of an alcohol, okay, ethanol, you're going to blow into an instrument, and if you have alcohol on your breath, it will actually convert. It's colorimetric, and for example, you may be converting orange to blue. Okay? If you blow in there and you don't convert any orange to blue, that means you have no ethanol. But if you convert a lot of the orange to blue, okay, and that can be measured by some type of light absorption, visible light absorption. If you do a lot of this, the authorities are going to assume you have a lot of alcohol on your breath, and based on how much blue you produce, you may be in some trouble. Okay, so a breath analysis test. Okay, let's show products here. Good old standard predict the product. Okay, you got an alcohol. You recognize you have a common oxidizing agent. What's going to be the product? All right. You don't really need to know the mechanism so much. This is predict the product. It's essentially memorization, yeah? The alcohol gets oxidized. You got to know bonding. Okay? I've seen plenty of students who know it gets oxidized, but then just can't draw the product. So you got to know the details of the bonding. We get oxidized to this ketone here, right? Secondary alcohol, it's oxidized to the ketone. I'll let you do the next one for homework. All right. One of the big three, aqueous sulfuric acid, essentially chromic acid, is going to oxidize the alcohol. All right. Other oxidizing reagents. All right, PCC. Let me go ahead and answer this one up here. Product here is going to be that carboxylic acid, right? Did you pause the video and do that on your own? Maybe I didn't give you enough time. Right? Primary alcohol gets oxidized to the carboxylic acid. Right? 5 carbons, 5 carbons. Please look at that, understand. What is the intermediate here? Okay, there's an intermediate before you get to the carboxylic acid, right? The intermediate is the aldehyde. All right. So it doesn't stop at aldehyde. Now, by the way, this up here should have had brackets around it. Whenever we have an intermediate that cannot be isolated, a neutral intermediate that's not isolated, if we want to show it, typically put brackets around it. And basically this just tells you that as this progresses from here to the product, the aldehyde is the non-isolatable intermediate. Now, what if you wanted to get the aldehyde? What if you wanted to oxidize a primary alcohol to an aldehyde and stop there? Can you do that? The answer is yes. You can use PCC for conversion of primary alcohols to aldehydes in good yield. PCC. Or these other two reagents. And this here would give, all right, the aldehyde. Now, of course, you can draw the product with the oxygen that way. Okay, either way, it's the same thing. Double bond there. All right, there's your aldehyde. Dichloromethane is a common solvent here. Okay, now importantly here, no H2O. And that's one of the main reasons it stops at the aldehyde, because remember, to further oxidize, you got to have water. If you keep it dry, don't use an aqueous solvent. Okay, we're using a dry organic solvent. PCC is pyridinium chlorochromate. That's actually shown on the other page. It's a complex ion and it's a pyridine cation. But it is soluble in organic solvents and does not require water. can be used without water. Thus, primary alcohols can be stopped at the aldehyde. Okay, and this illustrates a difference. If you take benzyl alcohol with one of the big three, you're going to get benzoic acid. But if you oxidize it with PCC, dry solvent such as dichloromethane, you're going to get the aldehyde, benzaldehyde. Now, of course, aldehydes can be oxidized to carboxylic acids. And we can look at that now. A common reagent for doing this reaction, which, by the way, the big three would do this, okay? The big three will take an aldehyde all the way to the carboxylic acid. All right? PCC will not. Well, maybe if you use water. If you added water, it would. Or the big three. But a specialized reagent that is common to oxidize in an aldehyde to the carboxylic acid is silver ion. Silver plus. And you often use ammonium hydroxide with it because it helps solubilize the silver ion. And the silver here is called the Tollens reagent. The Tollens reagent oxidizes aldehydes to carboxylic acids, but it does not oxidize alcohols. Okay? So it only does this here. The big three would do that there and also this. In this reaction, the silver ion gets reduced to silver metal. And metals are not soluble, and it will deposit, and the silver will look like a mirror on your flask, called a silver mirror. And if you get the silver mirror, you know the redox reaction took place. Just like if you get the blue color, you know the redox reaction up here took place. And so this is actually another indicator which can be used as a chemical test called the Tollens Test. And it can distinguish between aldehydes and ketones, because the silver will oxidize the aldehyde to the carboxylic acid, but remember, ketones cannot be oxidized. Not by the big three and not by silver ion. And conversely, the aldehyde will reduce the silver ion to silver metal, silver mirror, but the ketone will not. So if you have an unknown, okay, usually it's a liquid, could be a solid, but if you have an unknown liquid and you have decided it's either an aldehyde or ketone, well, you can treat it with the Tollens reagent, that is silver ion. Very often it's like silver nitrate, okay? Silver plus, okay? All this is soluble, but if you get silver depositing and it looks like a mirror, that's going to indicate that you have an aldehyde and not a ketone. I think that's the third chemical test we've looked at. All right. This is summarized here. Of course, esters would also give negative. The only carbonyl compound that gives a positive Tollens is aldehydes. Now, in biochemistry, you'll learn about the Benedicts test most likely. It's also a test for aldehydes to identify reducible sugars which contain an aldehyde group. Now, the Benedicts test, instead of using silver ion, it uses copper ion. And the copper 2 is reduced to copper 1, which is brick red. I've actually never done a Benedicts test, but I believe it's fairly common in biochemistry, and it's analogous to the Tollens test. Same type of considerations, results. A test for aldehydes, but you use copper instead of silver. Okay. What else was here? Of course, secondary alcohol with the big 3 is going to give the ketone. PCC would also give the ketone. But why use PCC, which is actually a little bit more expensive? There's no difference here. Up here you have a difference. The big 3 goes all the way to the carboxylic acid. PCC will stop at the aldehyde. Okay, because you're going to use it dry. Now, PDC is a variant of PCC or Tollens reagent. Okay, if you look that up on Wikipedia, you don't see these much anymore. Okay, but any of these 3 is typically going from primary alcohol to aldehyde. Okay. Should be some problems in the in your textbook. And I think that's it for oxidizing alcohols. Very common reaction of alcohols, yeah? And we had a green sheet which had some summary. That was the front, yeah? In the back, that's what we just did. Take a primary alcohol, one of the big 3, chromium or KMNO4. Aldehyde, here I showed brackets, right? Because it's further oxidized to the carboxylic acid. But with these guys, stops at the aldehyde. That doesn't mean you cannot, in a separate reaction, oxidize it. One of the big 3 would do that. Or a more specialized reactant would be the Tollens reagent. Secondary alcohol, one of the big 3. Or even one of these reagents here. I don't know why you would use one of these more specialized reagents, because in either case you're going to stop at the ketone, because ketones are not further oxidizable in this class. And of course tertiary alcohols are not oxidized at all in this class. Okay, in the next video we'll be moving to oxidations of alkenes. Have a warm up down here. And we have an outline in this same handout beginning here. On the summary page, we see different reactions here. And we also have the other handout, which shows some sort of board information. Okay, guys, oxidation of alcohols. By the way, when we get to test 3, we'll be looking at the reverse of this. Okay, that is going from carbonyl compounds back to alcohols, which of course is reduction. All right. So we'll look at the reverse when we get to carbonyl chemistry. Okay, guys.